Hello students of Kartika High School and Junior College. This is Seema teacher here for chemistry, and we are going to continue with our final session on solutions, session number 4. Okay, starting with colligative properties, we have seen that there are 4 colligative properties: vapor pressure lowering, freezing point depression, then boiling point elevation, and osmotic pressure. After this, we have already covered the 3 in the previous sessions. Now moving on to the last colligative property, that is osmotic pressure. Now before we go to osmotic pressure, first let's understand what is osmosis. Now if you see the diagram over here, you can see that a beaker is taken with 2 compartments here, you can see. Okay, now on one side, on the left hand side, you have water, that is pure solvent, and on the right hand side you have a solution which contains lower concentration of water, because it has solutes. You can see it has solutes dissolved in it. Okay, these are the solute particles here. So here if you see, this side is pure solvent while this side is your solution, and these two are separated by a semi-permeable membrane. Now what exactly is a semi-permeable membrane? Okay, a semi-permeable membrane is just like a filter, but it acts only like it allows only certain particles to pass through it. So here this particular semi-permeable membrane allows only the solvent particles to pass through it, while it blocks your solutes. So you can see there is movement only of the solvent from the left hand side towards right hand side. So then what is osmosis? Now osmosis is nothing but it is the movement of higher solvent concentration. So higher solvent concentration is on the left hand side here, while lower solvent concentration is on the right hand side. So you can see a movement of higher solvent concentration to the lower solvent concentration, and the water tries to equalize the concentration on both the sides until the pressure is too high. So how do we define now osmosis? So here same diagram you can just understand here. On you can see this side is showing you pure solvent, okay, while here this side is your solution. So you can see initially the level of your solvent was here, but slowly over a period of time the solvent has started to move from right hand side to left hand side, because here the concentration of solvent is higher while here the concentration of solvent is lower. So you have the movement from right hand side to left hand side here in this case, and you can see the level has slowly come down for the solvent over here. So we can define osmosis as the net flow of solvent molecules into the solution through a semi-permeable membrane, or we can also say it is the net flow of solvent, okay, or net flow of solvent from a dilute solution to a more concentrated solution through a semi-permeable membrane. So this is how we define osmosis. But we want to see what is now osmotic pressure. Okay, so let's understand now what is osmotic pressure. You can see here a beaker is taken with a thistle here. This thistle contains a solution. This is containing the solution here, and there is a semi-permeable membrane which is covered here. This is inserted into a pure solvent. So you can clearly see you have the solvent here. This is your solvent while this is your solution. So you can see after some time what happens. The solvent starts entering into the bottle here, and slowly the level rises. So you have some movement of the solvent inside the bottle. This will continue till an equilibrium stage is reached or till a pressure is exerted which will stop the flow of solvent. So this pressure which is stopping the flow of solvent is called as osmotic pressure. So at equilibrium what happens? The rate of the forward and the reverse passage of solvent becomes equal. So there won't be any movement and the height of the column will remain constant. So this shows that the hydrostatic pressure has stopped the osmosis. So how do we define now osmotic pressure? So the hydrostatic pressure that stops osmosis is called as osmotic pressure of the solution, and this hydrostatic pressure is equal to H rho G, where H is the height of the liquid column, rho is the density of the solution, and G is the acceleration due to gravity. Now let's understand one more process, that is osmosis. You have already understood. In osmosis you can see here in this case, first diagram, if you see the first diagram, you have the solvent over here and this is your solution. So you have the movement of solvent from this side towards, okay, towards your right hand side. But so this will stop at a when the osmotic pressure is applied here, okay, after some time. But if you apply an external pressure which is greater than the osmotic pressure, so what will happen is the solvent will now flow in the reverse direction. Means now the solvent will move from the solution towards the solvent. So this is called as reverse osmosis. Now this will only take place when you have an external pressure being applied over the solution. And generally this is used in cases of purifying of seawater. Okay, you can see the salt on this side, you have the salt water. Okay, you have the salt water which is your so basically your solution, and you have fresh water. Now when a pressure is applied on the salt water which is more than the external pressure, here you can see through a piston pressure is being applied, so automatically water from the solution, from the salt water solution, moves into the fresh water. So the pure solvent then flows from the solution into the pure solvent through a semi-permeable membrane, and this phenomena is called as reverse osmosis, just the opposite of osmosis basically. Now based on the concentration of solutions, we have three different types of solutions here. You have isotonic solution, hypertonic and hypotonic. What is isotonic? Iso means same. So when you have a solution in which the solute and solvent are equal, so the concentration of solute and solvent are equal, you say it is a isotonic solution. In case of hyper means more. So here we are talking in terms of more amount of solute. So if you have more solute and less solvent, you say it is a hypertonic solution. And similarly hypotonic, hypo means less. So when you have less a number of solute as compared to solvent, you say the solution is hypotonic. So now this can be used in comparison of two solutions with respect to your osmotic pressure. So isotonic solutions, so when you have two or more solutions having same osmotic pressure, we say they are isotonic solutions. Similarly, if two solutions have unequal osmotic pressure, now you have taken two solutions but they are having unequal osmotic pressure, and the one which has more concentrated solution, means more amount of solute than the other, is said to be the hypertonic solution. Similarly, the one which is the dilute solution, which is exhibiting lower osmotic pressure, is said to be hypotonic solution. Now, the relationship between osmotic pressure and concentration. So we know that the ideal gas equation is PV is equal to nRT. Now, if we substitute pressure with pi, pi here stands for your osmotic pressure, we can get the formula as NV is equal to nRT, and when you bring V down, it becomes pi is equal to nRT upon V. Now we know that N upon V is nothing but what? A molarity, that is concentration, which is denoted by C. So we can write the equation as pi is equal to CRT, concentration in molarity into R into T. You can see over here. So for a very dilute solution, the osmotic pressure can be calculated where pi is equal to N2RT upon V. N2 is your moles of solute. V is the volume of the solution in liters. N2 is the mole of non-volatile solute, and R is gas constant, while pi is your osmotic pressure. And we know that N2 upon V is concentration in molarity. Here we have taken it as capital M. So pi is equal to MRT. So you can write as pi is equal to CRT or pi is equal to MRT. Both are acceptable. Note now, just make a note here that the solute concentration, see if you see the previous cases, we have expressed concentration in terms of molality because they were temperature independent, but osmotic pressure is temperature dependent. So that is why here molar concentration is expressed in terms of molarity. Now let's see the relationship between, or how to find out molar mass through osmotic pressure. Now here we know that pi is equal to N2RT upon V. Now if you substitute the value of N2, that is number of moles, by W2 upon M2. W2 is the mass of solute and M is the molar mass of the solute. So you get the equation as pi is equal to W2RT upon M2V. And just rearranging the equation, you can write it as M2 is equal to W2RT upon pi V. Now this formula can be used in calculation of finding out molar mass of the solute. Now let's see a numerical based on this. What is the molar mass of a solute if a solution is prepared by dissolving 0.822 grams of it in 300 milliliter of water, which has an osmotic pressure of 149 mmHg at 298 Kelvin. Now first we need to know the formula. M2 is equal to W2RT upon NV. Then writing down the data what is given to you. So weight of solute is given 0.822 grams. Gas constant, mostly it will be if it is given, otherwise you will have to by heart it. That is the value of R is constant. Temperature is given to you 298 Kelvin. Now osmotic pressure here is given as 149 mmHg, but we want it in ATM. So just divide it by 760. So you will get as 0.196 ATM. Now why this conversion is required, if you see here the gas constant is given as ATM. Okay, so you should know from here itself that you have to do the conversion. Similarly, volume is given as 300 ml, which is to be converted into liters. So it comes to 0.3 liters. Now substituting all your data in the formula, you get the final answer. M2 is equal to 342 grams per mole. So you can calculate this entire equation using your log table. So finally we have seen that using colligative properties we can determine the molar mass using the first formula we had seen was in case of lowering of vapor pressure. Second was using depression in second was elevation in boiling point, or through depression in freezing point, or using osmotic pressure. But out of the four, osmotic pressure is much you can say more precise and a measurable property than the other colligative properties. Therefore it is used to determine the molar mass of most of the substances. Now, just your remembrance for whatever for formulas we have done up till now. So, molarity we know is what moles of solute dissolved in a liter of solution. It is denoted by capital M. Similarly, molality is moles of solute in a kg of solvent. It is denoted by small m. And how do you find moles? Moles is mass of solute in grams upon molar mass of solute. Normally, we take it as N2. You can make a note of all these formulas in your book. Similarly, molecular weight determination. The molecular weight determination can be done by using any of the four colligative properties that we have seen. Okay, so you have the using vapor pressure lowering, where M2 is equal to W2 upon W1, M1 into P, that is P10, that is vapor pressure of pure solvent upon delta P. Similarly, using boiling point elevation, we can find out molar mass by Kb into 1000 into W2 upon W1 into delta Tb. Or it can be calculated using freezing point depression, where M2 is equal to Kf 1000 W2 upon delta Tf into W1. Or it can be through osmotic pressure, what you saw just now, that is M2 is equal to W2 RT upon pi V. So I hope all the four colligative properties are clear with you, dear students. So you just need to revise and go through all the uh, four sessions that have been uploaded up till now, so that we can discuss the answer questions in the next session. Thank you.